Hello everyone, I am Van-Giang Trinh, postdoc at Marseille University. Today, I am pleased to present our latest result on Boolean network research, efficient enumeration of fixed point in complex Boolean network using answer set programming. I am very sorry because unfortunately for visa problem, I had to give my talk by video. A Boolean network include a set of inner nodes and a set of associated Boolean function. A time t x node can update its state by applying its Boolean function to the current state of the model. There are various update schemes, but to measure one is fully asynchronous. That means only one node is non-deterministically selected to be updated. And synchronous, that means all the nodes are selected to update. Let's see an example Boolean network in the last, and the right is the dynamics under fully asynchronous update scheme. It's not denotes a state, and it's as denotes a transition from a state to another state. An attractor is a minimal non-empty set of state. One enters this cannot escape from it. The example Boolean network under fully asynchronous update scheme has two attractors. One is the fixed point that it consists of only one state. Another one is a cyclic attractor that consists of multiple states. Attractor analysis has many applications in system biology because attractor correspond to biological phenotype. Apart from system biology, it has application in many other fields. Today, the analysis of fixed points remain a very useful and standard tool. First, in some cases, the full computation of cyclic attractor remain intractable. Second, for many biological systems, the expected long-term behavior is not cyclic. Third, fixed points are independent of the update scheme, while cyclic attractors are not. Finally, it is a starting point for state-of-the-art for computing cyclic attractor. Furthermore, it has more application in, for example, coding theory, control theory, and neural network. So in this work, we focus on fixed point enumeration. A fixed point can be characterized by this equation for every node VIs. We can easily see the relation to the subproblem. In this, the problem of detecting a fixed point is NP-hash. And the problem of enumerating on fixed point is number p-hash. This enumeration problem has attracted researchers from various communities, and many methods has been proposed. In practice, model size and the complexity of Boolean update function constantly increase. So the existing methods show their limitation. They all require intermediate representation of the original model, which are sometimes very hard to obtain, for example, flying beacons or DNF. In practice, the second method is only applicable for locally monotonic model. Answer set programming has been widely applied to the field of system biology. Naturally, ASP has been quickly applied to various analysis problems on Boolean network. To our best knowledge on the most recent and efficient methods for this problem, derive on answer set problem. With this motivation, we have proposed two new ASP-based methods for efficiently enumerating fixed points. Now let me introduce these methods. First, we propose a core ASP encoding such that its set of stable model one-to-one correspond to the set of fixed points. For each node Vi, we introduce two atoms Pi and Ni. The below's ASP rule ensures that a stable model corresponds to a state. And the generation is as follows. Recall that fixed point can be characterized by the conjunction of two paths, this one and this one, with equal term as ASP rules. To avoid default negation, we use the negative normal form of a Boolean function. We can easily obtain an NF by recursively applying the De Morgan laws until all negation that remain are on only literal. So NNF is much more efficient to obtain than DNF, CNF, or PDD. The ASP rule for the first part is as follows. For the case of disjunction, we need to introduce a new auxiliary item. And for SJs, we add the new rule. Then we have the similar rule for the second bus. We prove that the set of stable model one-to-one correspond to the set of fixed points. Recall the example Boolean network, which has only one fixed point. There is its ASP encoding written in clinical syntax. This rule ensures that a stable model corresponds to a state. The rule for the first part of node V1, second bus. Since the F2 is equal to F1, there are similar rule for node V2. Note that we exclude auxiliary item from stable model. This encoded ASP has only one stable model, P1, P2, which correspond to fixed point 1, 1. But there is a problem with short nodes. The Boolean function of a short node is an identity function. The number of fixed points may be exponential in the number of short nodes. In on the existing encoding, a rerouting stable model only corresponds to a single fixed point. This is usually a bottleneck, so we need a new method to overcome it. Let's consider an example Boolean network. The node V1 is a short node. This Boolean network has 3 fixed points with corresponding stable model there. Our main idea is to group two stable model A1 and A2 into a Hebrew model A. if they only differ in the atom corresponding to a short node. For examples, A1 and A2 only differ in the atom corresponding to short node V1. So they can be grouped to a Herbrand model A. Next, we add A to the set of stable model and then repeat the grouping process until there is no new stable model. This grouping process introduces more stable than before, but we can see A still cover all the fixed point represented by the two stable model A1 and A2. So we can return only A by considering only maximum set inclusion stable model. We modify the core encoding to make the above procedures fully automated in the ASP solver. First, we remove the condition. Second, we add choice rules to make Herbrand model A become a stable model. And finally, we prove that the set of maximal set inclusion stable model fully covered on fixed point of the Boolean network. Note, however, that a stable model A can be a stable model can be groupable with multiple ones, leading to one fixed point can belong to multiple maximal set inclusion stable model. So we use binary decision diagram to symbolically present the set of maximal set inclusion stable model. It can be a meta result for further analysis based on symbolic operator. We implemented the verbal methods in a Python tool called FASP. We use Clinko at the ASP solver. We had two methods. The first one is the core encoding, and the second one is the modification to handle the case of many short nodes. We compare our methods with four state-of-the-art methods. Note that our second method and the FP cluster are not able to control the maximum number of rerouting fixed points. We test our methods on real-world model from BPM repository. We also test on very large random model. Now let me show the result on real-world model. These figures show the number of shown model for each method for different time limits with respect to 1,000 first fixed point. There are only 4 methods for this time. We report some observation from the results. First, ANASP and FASP conjunction are comparable and they vastly outperformed by Boolean and MPPN. In particular, ANASP could not handle one model, but FASP conjunction could handle it within 10 seconds. Their result for the case of on fixed point. We have 6 methods for this time. We report some observation from the result as follows. ASP and FASP conjunctions are still comparable and still vastly outperform FP cluster by Punes and MPPN. Our second method shown more model than all the other methods on every time limit. The difference is the last from the time limit of 10 seconds. Next, we show the result on random model. There, the result for the K of 1000 first fixed point. First, by Punes could handle no model. It's always failed at the phase of computing flying beacon. Second, ASP could handle very few models. In small model, the number of transactions is very large. Interestingly, MPPN could handle more models than ASP. This can be explained by the fact that all models are locally monotonic, which is the advantage of the tool MPPN. Next, the FASP conjunction is the best method and is vastly outperformed the three other methods for every time limit. You can see. For the K of on fixed point for every model, on the comparison methods fail to obtain on the fixed point and very quickly miss the out of memory errors. The reason is that the number of on fixed point, even stable model for our second method is actually too large due to a loss of short node. So there is room for improvement. In summary, fixed points are important and standards in Boolean network analysis. We had proposed two new methods beyond ASP for enumerating fixed points. Both rely on negative normal form, a Boolean function, which are much more efficient to obtain than other representation used by previous methods. Our second method provides a more compact representation of the results based on binary decision diagram. Our methods vastly outperform on the state-of-the-art methods. In particular, our second method shows its superiority to all the other methods in enumerating on the fixed point of the model with many short nodes. Our second method exploits the unique characteristics of ASP, but it is possible to build a SaaS version for the first method. We can use the polynomial transformation like our first encoding or testing transformation, but this introduce auxiliary variable. The problem is that multiple redundant models may encode the same fixed point. So a step to eliminate redundant SAT model is needed, adding more complexity to the SAT approach. In the future, we will improve our second method to handle the case of many short nodes. In addition, it would be interesting to implement the SAT version of our first method and evaluate its performance. Finally, we will extend the proposed methods for computing chart spaces of Boolean network, which are more general than fixed point and are useful approximation for a chapter in Boolean network. My talk is finished. Thank you so much for your attention.